Hello everyone, welcome to my YouTube channel. Today I'm going to discuss Pearson Edexcel International AS level paper, January 2021, and the paper code is WCH13. This is 50 marks paper. Let's start from the question number 1. A student was provided with the 5 test tubes labeled A, B, C, D, and E, each containing a colorless aqueous solutions. So the 5 solutions were known to be. So these are the 5 different solutions. They were placed in the 5 different test tubes. So the student carried out a series of tests to identify which test tube contained which solution. So he's going to identify the nature of the solution by using different tests. Let me tell you about some important points regarding to your solutions by using your specification. Barium chloride is BaCl2, nitric acid is HNO3, potassium bromide is KBr, silver nitrate is AgNO3, and sodium carbonate is Na2CO3. So according to your specification, barium ions, potassium ions, and sodium ions, they can be tested through a flame test. So if this is Ba2 positive, and if we do the flame test, we will see the apple green color. So green flame will be there. K positive, that will produce a lilac flame. Na positive in the flame test, that will produce a yellow flame. Then H positive is the acid, and if we look at the acid, that turns uh, blue litmus paper red or universal indicator paper red. So it can be tested by using the universal indicator. So universal indicator will turn red, or if we test any acid that can produce the effervescence of carbon dioxide with the metal carbonate. So before going to our question, let me tell you about some important points so you people can easily solve this question. Now, there are some halide ion as well, chloride ion, bromide ion, and chloride ion, they can be tested by using aqueous silver nitrate. So we can test the chloride or bromide or iodide ion by using aqueous silver nitrate. So if we use the aqueous silver nitrate, chloride ion can produce the white precipitates, whereas the bromide ion, they can also produce the precipitates with the silver nitrate, but the color is different. They can produce the green precipitates. So if we have the iodide ion, they will give us the yellow precipitates. Now here there is a silver nitrate, so it means that you can use the silver nitrate to test both the aqueous solution of barium chloride and potassium bromide, in which the chloride ion, they will give us the white precipitate of silver chloride and green precipitate of silver bromide. Silver ions, we can say that the silver ions can be tested by using the aqueous solution of metal halides. We can test from sodium chloride, potassium bromide, potassium iodide, then we can get the different color of the precipitate. Here, the carbonate ion can be tested by using acid. So these are some informations regarding your specification. Nitrate ion are there. Okay, so nitrate ion, they can be tested by using aqueous sodium hydroxide and plus warm. So ammonia gas will be given off, which turns moist red litmus paper blue, or which produces the white fume with concentrated. It can turn the moist red litmus blue, or it produces the white fumes with concentrated HCl. So before starting question, Let's stop the video and learn all these cations and anions and then look at the question. Okay. Now, the student tested each solution using universal indicator paper. Only solution A turns the paper red. So universal indicator paper, when it turns red, this is the property of acid. So you have just one acid in this list. So nitric acid is the answer. So nitric acid can turn the universal paper indicator red. Then the next part, the student mixed 1 centimeter cube of aqueous solution of A. Now A is nitric acid with 1 centimeter cube of each of the other solutions. So there was no change for the three of the mixtures, but effervescence. If you have acid, as I have already mentioned, that the acid can produce the effervescence with carbonate. Was observed when solution A was mixed with solution C. So C must be carbonate. Check your list. Which one is the carbonate? Sodium carbonate. So any carbonate can produce the effervescence of carbon dioxide with the acid. So the solution C is sodium carbonate. Write an ionic equation for the reaction between solution A and solution C. Solution A is nitric acid. Solution C is sodium carbonate. So metal carbonate, they react with the acid to form carbon dioxide, salt, and water. So let me write down the complete equation. Sodium carbonate, it reacts with the nitric acid to get sodium chloride, water, and carbon dioxide. So this is the balanced chemical equation. So if you want to convert into the ionic equation, we have to skip the spectator line. So Na positive to Na positive on the left hand side, then 2Na positive on the right hand side. So these are the spectator lines. So after skipping 2Na positive, carbonate CO3 2 negative will left behind. Then 2NO3. Okay, we will get the sodium nitrate here. Instead of chloride, we'll get the sodium nitrate. Okay, so NO3 negative spectator line. So we can cut the 2NO3 negative. Then we will get 2H positive. On the right hand side, Na positive and NO3 negative both are the spectator ions. So by skipping those ions, we'll get H2O plus CO2. So this is the ionic equation for the reaction between metal carbonate and acid. This is the complete equation. So we can use the complete equation to get the ionic equation. Okay, look at the next part. The student then mixed 1 centimeter cube sample of the remaining solution as shown in the table. The student mixed B and D, no change, B and E, B and D and E. So we're getting the cream precipitate. So in your specification, the cream precipitate of, they are of silver bromide and white precipitate silver chloride. We can also use the lead 2 nitrate as well, but we'll get the same color precipitate. So it means that E is the common reagent which is producing the cream precipitate with D and cream precipitate with B and white precipitate with E. So E must be silver nitrate. So E is silver nitrate because silver nitrate produces white precipitate with chloride and cream precipitate with bromide. So if we look at the B, B must be the compound of bromide. So let's see that which one is the bromide. Okay, so potassium bromide is the compound for the which contains the bromide, and barium chloride is the compound which contains chloride. So cream precipitate mean there must be a bromide. So we can say that the B is potassium bromide. And solution D is barium chloride. Okay, now the next part is three of the cations in the compounds in A can be identified using flame test. Now we're going to identify the presence of cations by using the flame test. Cations formula, as I have already mentioned, that the potassium ion, sodium ion, and barium ion in this list, they can be identified through the flame test. So if we have a Na positive ion or A positive or Va2 positive, we can test these positively charged ions from the sample as a flame test by observing that they will produce the different color. Na positive, that can produce the yellow or orange flame. E positive, that will produce the lilac flame. And Ba2 positive, it produces the apple green or light green flame. So this is about the question number one, that every substance that can be identified by using the salt analysis. Now, if we move to the next question, this is question number two, in which the sodium hydroxide solution reacts with the carbon dioxide in the air and should be standardized before use. Ethane dioic acid may be used for this standardization, and a standard solution of ethane dioic acid is prepared. So now the first task is that to prepare the standard solution of ethane dioic acid. Standard solution is that solution having non-concentration. Now, 2.40 grams of solid ethane dioic acid is dissolved in approximately 100 centimeter cube of deionized water in a beaker. So this is a beaker in which 2.40 gram of ethane dioic acid, they are mixed with 100 centimeter cube of water. The solution is transferred then. If we mix, we will get an aqueous solution of ethane dioic acid. Now this solution is transferred to the volumetric flask. The total volume of the volumetric flask is 250 centimeter, and here must be a marked line. So if we shift the 100 centimeter cube of the solution of ethane dioic acid, which contains 2.40 gram, into the volumetric flask, then make up to the mark with deionized water. Now the first question is that give a possible reason why any solution remaining in the beaker is washed into the volumetric flask before making up to the mark. Now we have to shift all the amount of ethane dioic acid, which was dissolved in 100 centimeter cube, into the volumetric flask. So if we skip this point, what will happen? All the solid, which was actually weighed out to make this solution, should not shift it to the flask. So it means that we must shift all the solution to the flask. So all the solid weighed out to make solution should be shifted to the flask. Or we can also say that none of the solution of the acid left behind in the beaker. Left behind in the beaker. So this is the alternate answer. We should write one of them. The next part is calculate the concentration of this standard solution of ethane dioic acid in moles per dm cube. Give your answers to the appropriate number of significant figure. A molar mass of ethane dioic acid is 90 grams per mole. If we look at the formula of the concentration, the unit gave us the idea that if we want to calculate the concentration in moles per tm cube, this is actually the formula: moles per tm cube, moles over volume, and the volume must be in tm cube. For calculating the concentration, we must have moles. Now, if we look at our question, 2.40 grams of ethane dioic acid, which was in the solid state, dissolved in 250 centimeter cube of water. 2.40 plus 250 centimeter cube of solution was there. So we can convert the grams into the moles. So first of all, calculate the moles of ethane dioic acid. So 2.40 grams over 90 mass over mR. So we'll get 0.0267 moles. Then we can go for concentration, which is in moles per dm cube. We have the moles 0.0267. Then the volume is 250 divided by 1000. The volume is in centimeter cube, so we should convert into dm cube. So this will become 0.1066, or this is approximately equal to 0.11 moles per dm cube. So these are the appropriate number of significant figures. So we can get the idea about the formula of the concentration from its unit. The unit is mole per dm cube. So mole is N and the volume is in dm cube. So N by V is the concentration formula. So this is the way that we can get the concentration of ethane dioic acid. Okay, now the next part. Now a different standard solution of ethane dioic acid is used to determine the concentration of sodium hydroxide solution, J. We have the flask and the burette. Just check the procedure. A burette is rinsed with the deionized water before starting our experiment. This was done. A burette is then rinsed with 0.090 moles per dm cube ethane dioic acid. Ethane dioic acid having the concentration 0.0900. A pipette is used to transfer 25 centimeter cube portion of the solution J. So 25 centimeter cube of J that was shifted into the conical flask with the help of pipette, and then 0.0900 moles per dm cube concentration having concentration that was shifted into the burette. The portions are titrated with the ethane dioic acid solution using phenolphthalein indicator. So we are using the phenolphthalein as an indicator. Explain why the burette is rinsed with the ethane dioic acid solution in step 2. So step 2 is that the burette is then rinsed with this. We're going to take ethane dioic acid in burette. So before taking ethane dioic acid, this burette was actually rinsed with ethane dioic acid. We're going to take the solution and we are rinsing with the same solution. Why we're doing that? Actually, to stop the dilution of the acid. This burette may contain some amount of the water and that can dilute your solution. So why we're doing that? To stop dilution of ethane dioic acid. Or we can also say that we are doing that to remove remaining water from the burette. So this is the alternate answer. Then the diagram shows how the student read the filled pipette in step 3. We're taking the colorless liquid ethane dioic acid in the burette. So for the colorless liquid, if we have any colorless liquid, we should choose the lower meniscus. for its reading. We should use the lower meniscus for colored liquid. We can use the upper meniscus for reading. So this is an important point. Identify the two mistakes in the student made. So in the burette or in the pipette, if we want to take the reading of a colorless liquid, we should use the lower meniscus. For colored liquid, upper meniscus. So as we're using the ethane dioic acid, which is a colorless liquid, so what are the two mistakes? Number one, bottom of the meniscus should be marked. Okay, we should actually, he has marked the upper meniscus. So he should mark the bottom of the meniscus. So the number one mistake is that bottom of meniscus should be marked. Should be marked as we are using the colorless meniscus. And the second thing is that eye level should be at the bottom of the mark or meniscus. So eye level should be at the bottom of meniscus. It should be in front of this. We can see in front of this. It should be in front of this mark. Okay, next part. The student completely emptied the pipette for each transfer in the step 3. So explain the effect on the titre. Acid is using as a titre of completely emptying the pipette. We have taken the J in the flask rather than leaving a small portion of the solution in the tip. So what will happen if we do that? So this was taken in the flask and the titre is in the acid. So explain the effect on the titre of completely emptying the pipette rather than leaving a small amount of the solution in the tip. Now what will happen? Then there will be too much solution J in flask and the value of titre definitely will increase. And the value of titre will increase. State the color change in the conical flask. In the conical flask, the J solution is there and we are titrating against acid. So in the base, the color of the phenolphthalein indicator is pink, and in the acid, it is colorless. So this is the color change from pink to colorless. Now these are the titration results in the table. Titers used in calculation of mean. So you have to take the difference of these numbers. This is 25.05, 25.05 minus this. So if we take the difference of these numbers, so the values are 24.60 for this and then 24.50. The titers used in the calculation of means. So these two titers, they can be used because these are the two concordant readings. Concordant readings must have a difference up to 0.2, not more than that. So complete the table and calculate the mean titer. So we can take these mean titers like 24.60 plus 24.50 divided by 2 to calculate the mean titer. And this is 24.55. So this is the mean titre, which is can be calculated by using concordant readings. Okay, now calculate the concentration of sodium hydroxide solution in moles per dm cube. The equation for the reaction or the titration is this. So first of all, we know that the uh, ethane dioic acid is its concentration is 0.0900 in the question, and the mean titer is 24.55. So the volume of the sodium hydroxide that was taken 25 centimeter cube. 25 centimeter cube was shifted, I think. Let's check. Okay, 25 centimeter cube. Then now, first of all, we can calculate the moles in ethane dioic acid. So moles in ethane dioic acid. Moles are concentration into volume. So the concentration is 0.0900 multiplied by the volume is this, and we can convert it into dm cube. So this is, I think, 2.2095 times 10 raised to power minus 3. Now we can calculate the moles of sodium hydroxide from the stoichiometry of the equation. As we can see that the 1 mole can react with the 2 moles of sodium hydroxide. We are going to calculate the concentration, so that's why we're using the stoichiometry or the molar ratio of these two reagents from the balanced chemical equation. So if we make it 2 times, we will get the moles of sodium hydroxide. Then 4.4 times 10 raised to power minus 3. So to get the concentration of sodium hydroxide, concentration is moles over volume. So volume must be in dm cube. Now the moles are 4.4 times 10 raised to power minus 3 over the volume is 25 and convert it into dm cube. So we'll get the concentration of sodium hydroxide, which is 0.18 moles per dm cube. So this is the concentration of sodium hydroxide. Okay, now like now look at the question number 3. This is the question number 3. This question is about the thermal decomposition of group 2 carbonates. A student heated a sample of group 2 carbonate until no more gas was produced. And this is the apparatus construction that this is a group 2 carbonate, decomposes to give metal oxide and carbon dioxide. So this is a metal carbonate heated. There's a test tube, then a delivery tube, then there is a measuring cylinder having 250 centimeter cube of volume, then the water tub or water trough. Give a reason why the delivery tube must be removed from the water bath before removing the test tube from the heat source. So this test tube is heated and the metal carbonate decomposes to give metal oxide and carbon dioxide passes through this delivery tube and that can be collected in the measuring cylinder. So this is a hot tube and this is the water at normal temperature. So if we remove the heat source, this cold water that may rush into this hot tube and it may crack this tube. So this is technically the suck back problem. This is the suck back problem. So we can say to stop the suck back problem, or we can say that the cold water, or we can say cold water rushes in a hot test tube and may crack. So this is the reason. Now, let's move to the next part. So the results of the experiments are shown. The volume of the carbon dioxide that was produced is 95 centimeter cube. Mass of the test tube plus carbonate 21.69, and mass of the test tube was 21.36, and mass of the carbonate is 0.33. So this is the difference of these two values. So we have 0.33 grams of metal carbonate, and we are getting 95 centimeter cube of carbon dioxide gas. Now, what to be done with these values? Okay, using the results of the experiment, identify the group 2 metal. So we're going to use the results of the experiment to identify the group 2 metal and the information that the molar volume of the gas at room temperature and pressure is 24.0. This is the equation that metal carbonate decomposes to give metal oxide plus carbon dioxide. We are getting a 95 centimeter cube of carbon dioxide, and we have the mass of 0.33 grams. So if we want to identify this metal from the metal carbonate, we must have the MR values. If we know the MR, so we can identify this metal. And if we use this formula, N is mass over MR, or MR is mass over moles. We have the moles, but we have the mass, we don't have the moles. So if we know the value of moles, we can get the MR. So if we know the MR, we can easily get the metal from the metal carbonate. So to get the moles of metal carbonate, we have the information about carbon dioxide. So first of all, calculate the moles of carbon dioxide. Then use the stoichiometry of the equation, molar ratio in the balanced chemical equation to calculate the moles of metal carbonate. Then use this formula to get MR, and MCU3 is equal to the MR, then subtract the sum of sum of the carbonate from that value, you will get the M and identify from the periodic table. Okay, I'm going to do in front of you. Now, first of all, calculate the moles of carbon dioxide. Then you can calculate the moles of metal carbonate. We can't use the formula mass over MR because we don't know which metal is there. So 95 divided by 24,000, we'll get the moles in carbon dioxide. So this value is 3.958 times 10 raised per minus 3. So these are the moles which are present in 95 centimeter cube of carbon dioxide. Carbon dioxide and metal carbonate, they're present in 1:1. So that's why the same number of moles of metal carbonate. Then the calculate the MR of metal carbonate. This is the formula. So MR is mass over moles. Mass 0.33 divided by moles are 3.958 times 10 raised per minus 3. So the MR is 83.5. Now, this metal carbonate is 83.5. So if we look at the metal carbonate is 83.5. If we want to identify the metal, now we can use the relative AR values of the carbon and oxygen. So this is 12, this is 16 times 3, then 83.5. So metal M is 83.5 minus 48 plus 12, 60. So the AR of the M is, if we subtract these values, we can get the AR, which is 23.5. So we can use the periodic table to identify this, but mostly here the student can do the mistake. Now, mostly the 23 is used for sodium, but this is not sodium because this is the group 2 metal carbonate, and group 2 metal carbonate is 23.5. If it is 23.5, it must be magnesium. because magnesium is 24. So this value is close to the magnesium. So that's why the metal in the metal carbonate is magnesium. Because if you have the metal 1 carbonate, so this formula must be like M2CO3. Now this formula is MCO3. This is in group 2 as already mentioned in the question. So that's why the answer is magnesium instead of sodium. Now there is another question that the student suggested that the experiment could be made more accurate by increasing the mass of the carbonate from 0.33 to 1.0. No changes to the size of the apparatus or the method of the measurement of the gas produced would be made. Comment on this suggestion. So if we use the more mass, definitely we can decrease the percentage error. Okay, so the first comment uh, or the suggestion for this is that uh, this is used to decrease the percentage error. And the second thing is that if we use the more mass of the metal carbonate, so the volume of the carbon dioxide would be more than the volume of the mating cylinder. We are using the mating cylinder of 250 centimeter cube in this experiment. So the volume of carbon dioxide would be more than the volume of mating cylinder. So we can check that if we have let's say we have the 1 mole of magnesium carbonate. So 1 divided by the MR 84.3, 84.3 was the MR. Then this is 0.01186. So if we convert it into the volume, 0.01186 times 24,000, now we are getting 284 centimeter cube of carbon dioxide, which is the more than the volume of the apparatus because we are using the mating cylinder having 250 centimeter cube volume. So if we increase the mass, no doubt that will decrease the percentage error, but it will produce the more amount of the carbon dioxide, which is more than the measuring cylinder. We're using the measuring cylinder to measure the volume of the carbon dioxide, and if we are getting more volume than the capacity of our instrument or the measuring cylinder, definitely that is not possible for us to collect all the amount of gas. Then this part is regarding the energetics. So the enthalpy change for the thermal decomposition of carbonate uh, is difficult to measure directly. So an example of the Hesses last cycle to determine it indirectly. So this is a metal carbonate. Decomposes to give metal oxide and carbon dioxide. Here, the metal carbonate reacts with the hydrochloric acid to give these products. Then metal oxide plus carbon dioxide, they can also produce with HCl. They can also produce these products. So in an experiment to determine the delta H1, so here we're going to, first of all, we're going to determine this 0.050 moles of metal carbonate. We have 0.050 was placed in a 100 centimeter cube of beaker. This is the volume of the beaker. We're not going to use this. 60 centimeter cube of 2.0 mole per dm cube hydrochloric acid. This hydrochloric acid is 60 centimeter cube, the volume, and the concentration is 2.0 mole per dm cube. Then this is in axis, so hydrochloric acid is in axis. So we have to use the moles of MCO3 at the end. Was added and the mixture was stirred and the maximum temperature, that was 6. Heat capacity of the solution. These are the extra informations that 4.18 joules per gram per degree Celsius, density of the solution, 1 gram per centimeter cube. Calculate the enthalpy change for the reaction between MCO3 and hydrochloric acid. So we're going to calculate the enthalpy change of this reaction, delta H1. Now, the formula for the enthalpy change is enthalpy change is heat transfer over moles. But first of all, we have to look at the heat transfer. or Q. So this is the formula mc delta T. Now, m is the mass of water or mass of the solution. So we have the mass of the solution, that is 60. Then C is given, which is 4.18. And then the delta T is there, 6.0. So this value is in gram. 4.18 is joules per gram per degree Celsius, and this is in degrees Celsius. So degrees Celsius and degrees Celsius, we can cancel this grams. So the answer must be in joules. So if we have the answer in joules, we can convert it into kJ. So 1504.8 joules, and we can convert it into kilojoules. So this will be 1.5048 kilojoules. So this is the heat transfer when we have 60 centimeter cube of 2.0 mole per dm cube hydrochloric acid, which was in excess, and it was added into 0.05 moles of metal carbonate. Now, the enthalpy change is the heat transfer over moles, heat transfer over moles. Now, here the student uh, should check that whether the moles of metal carbonate or the moles of hydrochloric acid can be used. We can calculate the moles of hydrochloric acid, that 2 times 60 by 1000. Here you get the moles of hydrochloric acid, but we're not going to use this. Why? Because in the question, the hydrochloric acid is in excess, and whenever you have the reagent in excess, and the second reagent must be the limiting reagent. So always use the moles of limiting reagent, because that will give us the accurate value. So 1.5048 divided the moles of the limiting reagent, and metal carbonate is the limiting reagent, so 0.050. So we will get 30.096. Then you have to put a sign as well. As you can see that there, if we are going to do this experiment, so the maximum temperature rise. So the temperature increases, so this value should be negative. You can use the negative sign at the start of this heat transfer as well. So this negative sign indicates that the overall reaction is exothermic. Now we have the value of this part. This is negative 30.096. We have the value of this part as well, which is negative 150. So we can calculate the value of thermal decomposition of metal carbonate. Now, using the answer to this, calculate the enthalpy change for the thermal decomposition of metal carbonate. So we have a triangle like that. Yeah. So we're going to calculate this value. This value is negative 30.096, and this value is negative 15. So Hesses law says that if your reaction takes place in one step or in several steps, the overall enthalpy change remains constant, or the enthalpy change is independent by the route which is taken for the chemical reaction, as long as the initial and the final conditions are constant. So this is the first route, and this is the second route, or this is the first route, or this is the second route. So in the first route, negative 30.096 is equal to x plus minus, and I think this is 150. 150. So negative 30.096 plus 150 is equal to x, and you will get the answer, which is 120. And this answer is in positive. So this enthalpy change is in positive. Okay, now there is another question. Now this question is, The halogenoalkanes. The halogenoalkanes, 2-chloro-2-methylpropane, may be prepared from 2-methylpropane to ol. So this is the procedure, step 1, 2, 3, 4, 5, 6. You can stop the video and look at the procedure. I'm going to solve the part first. Now, the concentrated hydrochloric acid used in the step 1 was labeled. The two safety precautions other than wearing safety and okay. Now, the safety precautions, as you can see from these signs, we should use the gloves. And then whenever we are using the experiment relating halogenoalkane, we can use the fume cupboard as well. Explain why the product in the organic layer in step 2 does not mix with the aqueous layer. So let's see the step 2. Two distinct layers form. The upper organic layer contains the required product and the lower aqueous layer is removed using a separating funnel. So here we have the organic layer and the aqueous layer. So they are not mixing with each other. So this solubility is linked with the intermolecular forces which are present between the substances. So the organic layer that contains the halogenoalkane, organic layer that contains the halogenoalkane, and aqueous mean water. Aqueous mean there is a water. So if we look at the nature of these two compounds or these two substances, the halogenoalkanes, they have the bond like this in which the halogen is partial negative. Now the carbon is partial positive. Whereas in the case of water, water is also this type of compound, but the halogenoalkanes, they are attracted with each other through the dipole-dipole forces. I mean, this is a dipole, and if we make another halogenoalkane, so these halogenoalkanes, they are attracted by dipole-dipole forces. So these are the dipole-dipole forces, and the water molecules through hydrogen bonding. So hydrogen bonding is comparatively strong intermolecular force than dipole-dipole forces, or we can also say the van der Waals forces. Now, if the halogenol if it is mixed with this, there must be a new attractive force between halogenol and hydrogen water molecules. So these van der Waals forces are not strong enough to overcome the hydrogen bonding between the water molecules. So that's why this happens. So we can say that the van der Waals forces between halogenoalkanes are not strong enough to overcome the hydrogen bonding between water molecules. The next part is state why the tap of the separating funnel must be opened in step 3. Let's check the step 3. Add solution of sodium hydrogen carbonate to the organic layer, then swirl gently, stop the separating funnel and shake it, invert the separating funnel and open the tap. Okay, so in this, the carbon dioxide is produced. So to release the pressure of the carbon dioxide, this is done. So we can say to release the pressure of carbon dioxide in the separating funnel. So this is done in the separating funnel to release the pressure of the carbon dioxide. State why anhydrous sodium sulfate. Anhydrous sodium sulfate, when we say that it absorbs water to become hydrated. So anhydrous compounds generally they are used as a drying agent. So anhydrous sodium sulfate, calcium chloride used as a drying agent, or it is used to remove water. Then draw the apparatus required to distill the product and collect the distillate. So the apparatus, look at the apparatus. Okay, let me tell you the apparatus. Okay, so this is the apparatus which is we used for the distillation. You must have a flask here, the tripod stand, then heat source, flask, thermometer. This is the Liebig condenser, water in, water out. This is a receiver, beaker. This is the apparatus which is used for distillation. So you have to draw this apparatus. This is a 4 marks, drawing and labeling. So if you draw this apparatus distillation, you should have the idea about the labeling of the apparatus as well. Okay, so the next part. Okay, the equation for the reaction is this. This is a reaction between our reagents. Uh, this is reactant like this. CH3, CH3, and CH3. It reacts with the HCl to get this OH is replaced by Cl. So the final product after distillation, weight 2.62 gram, calculate the percentage yield. So to get the percentage yield is the formula is actual yield over theoretical yield times 100. Now, the final product, the percentage yield of the product is calculated, and percentage purity, if we talk about the percentage purity of the reactant, and percentage yield of the product. So this is the actual yield. So 2.62 grams is the actual yield. We don't know the theoretical yield. So first of all, we have to calculate the theoretical yield. If we look at our question that how much amount of the different reagents were there. Just look at the grams. Okay, so 8 grams of 2-methylpropane 2-ol in the conical flask. So we have taken the 8 grams. So we have to use the 8 grams. Okay, so we have used the 8.0 grams and calculate the mass of this substance produced. Then we will get the theoretical yield. So we can go for moles as well. The moles of this alcohol. This is the tertiary alcohol. We have the 8.0 gram and calculate the MR of this compound. That is 74. This alcohol, tertiary alcohol, if you calculate the MR, this is 74. So the moles are 0.108. Now we can calculate the moles of this tertiary halogenoalkane. As you can see that tertiary alcohol and tertiary halogenoalkane, they're present in 1:1. So that's why the moles are same, 0.108. Now we can convert these moles into mass. So 0.108 times the MR of this compound. The MR is 92.5. So 92.5 is the MR. So 9.99 grams, approximately 10 grams. So this is the mass of uh, tertiary halogenoalkane, which is obtained by reacting 8 grams of tertiary alcohol with HCl. So this is the theoretical yield. We were expecting 9.99 grams, but actually we obtained 2.62. So to get the percentage yield, this is our actual yield. We got this much amount, but we were expecting to 9.99. This is theoretical yield time 100. So we can convert it into the percentage. So this is approximately 26.22%. So this much amount is the percentage yield. Now, let's move to the next part. So the chloroalkanes produced is used in an experiment to compare its rate of hydrolysis. So in this reaction or in this question, he's going for the rate of hydrolysis. The student dissolves separate 1.0 centimeter cube sample of each of the halogenoalkanes in ethanol and adds 2 centimeter cube of aqueous silver nitrate. So aqueous silver nitrate is the reagent which is used to identify the halogen or the halides. So this 2-chloro-2-methylpropane, let me draw some structures. So this is propane, 2-chloro, this is 2-chloro, then 2-methyl, 2-methyl. So this is the structure of 2-chloro-2-methylpropane. 1-chloro-2-methylpropane, this is propane. 1-chloramine, chlorine is present on first carbon, methyl 2, methyl is present on second carbon. So this is the structure of second compound. 1-bromo-2-methylpropane. Okay, this is the propane. 1-bromo, this is 1-bromo, this is 2-methyl. So this is the structure. So these are the three compounds. Sorry, 1 and then 2. Okay, so these are the three compounds. Uh, mm, what to do with that? The student concludes that both the structure and the halogenoalkane and the identity of the halogen affect the rate of hydrolysis. So the structure and the halogenoalkane, they can affect the rate of hydrolysis. Okay, just look at the structure. This is 3-degree halogenoalkane. This is the tertiary halogenoalkane, which contains CCl bond. This is 1 degree, or this is the primary halogenoalkane. And this is also primary halogenoalkane. So the structure is that tertiary, primary, primary. Then halogenoalkane, this contains CCl bond. This also contains CCl bond and this CPR bond. So rate of hydrolysis, that depends upon whether the structure is tertiary, primary, or secondary. And the second thing is that which bond is present there, CBr, CCl, or CIL, like that. Now, if we look at the results, this is the tertiary, this is the result for tertiary, and this is these are the two results for primary halogenoalkanes, but they have the different halogeno. Here you have the 1-chloro, here you have the 1-bromo. So we can see that the time and the time 5 and then 3 20 seconds and 4 20 seconds. So rate is actually inversely proportional to the time. We can say that as we can see that the fastest reaction in this and then the slowest in 1-bromo, and this is at the middle. So we can say that the rate is inversely proportional to time. So rate is inversely proportional to time. Now look at the nature of the compounds. The 2-chloro-2-methylpropane is tertiary. You have to explain in the terms of structure that 2-chloro-2-methylpropane is tertiary structure. So this is tertiary structure or tertiary halogenoalkane. shows faster reaction than rest of the two primary halogenoalkanes. So generally, we can say that the tertiary halogenoalkanes, they show the fast or quicker reaction as compared to the primary, but the rest two structures are primary. So we can differentiate these two structures on the nature of the strength of a CX bond. So one chloro 2-methylpropane, it takes more time, and one bromo 2-methylpropane, it's take less time. So if it takes more time, the CX bond is strong. So one chloro 2-methylpropane propane contains strong CCl bond, then one bromo 2-methylpropane which contains CBr bond. So CBr bond requires less heat energy to break. You can see that it takes less time. CBr bond requires less energy, to break. So this is all about this Pearson Edexcel paper. Thank you.